Hello everyone, this is Dr. Usuf Rahaman from Madanapalle Institute of Technology and Science. I am working as assistant professor since last 4 years. We have already discussed in our previous 2 lectures about Schrodinger equation, how it got developed, and also we discussed how we can simply derive the time independent Schrodinger equation. Now, in preceding lectures, in this particular lecture, we're going to discuss about time independent Schrodinger equation, a equation which is static, which is not varying or which doesn't extensively or exclusively include time in it. Now, why it is essential? Because solving altogether position and time in a differential equation is not an easy job. So we can separate out the time part and position part separately and can solve for wave function part which is totally position dependent in one part, another one is totally time dependent on part. Then we can find out in it. We're going to follow up a very easy way, or a very sophisticated also you can call it, way to find out time independent Schrodinger equation. Okay. Whatever discussions we will have, different kind of problems we're going to solve, we're going to use it, the time independent Schrodinger equation for that. We'll find out it's very fascinating that only solving time independent Schrodinger equation for particular cases, you can find out the time evaluation also, time evolution of that wave functions, or also particle of that, of the particle also. Now we're going to discuss which is time independent Schrodinger equation. Okay, so we're going to follow the variational way, or separation of variable method. Actually, we're going to use the separation of variable method. Separation of variables method actually to find out it. Okay, separation of variable method. Now, we all have gone through the discussion of time dependent Schrodinger equation. How the time dependent Schrodinger equation look like? So the time dependent Schrodinger equation is given as how it is written. The time dependent Schrodinger equation is minus h bar square upon 2m in one dimension. We are going to, for simplicity, we are taking one dimension, del upon del del x square, and this is function of position and time altogether, plus we have a potential which is also function of position and time altogether. Then we have the wave function operating on, then is equal to minus I h bar del psi upon del t, which is also function of position and time. This is in one dimension. Now, for a static case, we are going to consider that our wave function, we assume that our wave function, that is capital psi xt, is a product of a wave function which is only function of psi, so only function of position, that is small psi, and a product with another function, only function of time. Okay, so this is the method is followed when you are going through a separation of variable method. Also, let's call it equation number 2. Also, we consider as vxt, which is potential, which is only function of position, because most of the cases in quantum mechanics, so the systems we're going to discuss, the potential is not dependent of time, it is independent of time. So we are, for most of the cases, we are going to discuss the position only, your potential dependent only on x or position. Now we'll just simply put equation number 2 into equation number 1. We're going to easily solve or reduce the whole equation into 2 parts. One is position dependent, another one is time dependent. Okay, so how we can do this? I will substitute from equation number 2 into equation number 1 this whole psi xt. So combining or putting equation 2, so we can write putting psi xt from equation 2 into equation 1, what we will have? We'll have in that place we'll write all in place of psi x2 we'll write just these two product. Okay, so del square upon del x square will have psi of x multiplied by phi of t, just substituted in place of this function. We have substituted all multiplication together. Now in place of vxt, what will we write? We will write vx only. Then in place of psi xt, we will write small psi x phi t. Okay. Then we will have here minus my mistake. I h bar del psi of xt del upon del t as a total function of psi of x phi of t. Okay. Now observe one thing here. This is only the space derivative and this is only the time partial derivative. So whatever we have inside which is not dependent on space will come out as a constant, and here also whichever is not dependent on time will come out as a constant. So this will follow up here as can follow up this thing from here to here. So what will you get here? You can write here minus h bar square upon 2m. Here psi x will be operated by del psi square, but phi t is constant. So we'll write as phi of t as out, and we'll write del psi upon del x square as a function of x, plus here it will not change anything. We'll have psi of x and phi of t equal to what will happen here. Similarly, I h bar is a constant. Where we have phi t will be operated on by this single derivative, and psi x will come out. So psi x will come out as, and then we have del phi t upon del t. Good. Now, if we divide the whole expression by this whole multiplication of psi xt and phi xt, what will you get? If we divide this whole expression, we can call it equation number 3. So dividing equation 3 by psi of x phi of t, what will you get? We'll divide it. So we'll have del h square upon 2m. If we divide, what will happen? This part will be divided out, and we will only left with this in denominator, and we'll have del psi x del t. Here we will not have any function. Both of will be taken divided out, and we have this, and here psi x will be divided out. We'll have 1 upon phi of t, del phi upon del t. Okay. Now if you observe this equation properly, this part is only position dependent. This part is only time dependent. So we have an equation where one side is completely position part, another side is completely time part. So it's only varies with position, it's only varies with time, and it is collectively can be true only when both side is equal to some constant. Let's say call it E. Why we are calling it E, we'll know later. You can understand also this Vx is actually energy, potential energy. So whatever it will be equal to, it should also have a dimension of energy. It should also have a dimension of energy. So that's why we are putting it A. We'll know that later that this is actually energy. Okay. Now what we can write from this equation, we can write as it can be segregated. So it can be separated into two different equations. One equation with position part equal to E, and the time part will equal to equation of E. So we can have two equations from there. So equation 4 can be written into two separate equations. What are those? The right side part, what you can take as, we can write as, the left side part we can write as this. So let's say talk about the right side. Sorry, h bar square upon 2m del square psi x del x square plus v of x psi of x equal to e of psi x. Okay, and the other equation can be written in two equations. And what is the other equation? It can be written as I h bar del phi del t equal to e of phi t. Equation number 6. Okay. Now this equation number 5 actually known as time independent Schrodinger equation. We'll write in a different form although, but let's discuss this equation first. What is this? Now, if you recall, the total wave function we have written as a product of a time part and a position part. If you solve this equation, we'll get a solution which is psi x, and if you solve this equation, we'll get a solution which is phi t. If you solve the equation 6, the solution of equation 6, what is the solution? We'll get a solution of such kind that phi of t is some constant. Let's say you can call any constant, let's say call b, then e to the power I e upon h bar t. We get a solution of, sorry, minus I e h bar e upon h bar into t. So this solution, if you can find out, this is an oscillatory solution, and if whenever there is oscillation in a function or in a wave, what is there? It has a frequency, and how we know that frequency varies? Equal to h bar nu. So what will be the frequency then? E upon h bar. Now if you see it here, this is representing frequency. So that constant we have taken basically is the energy of the particle. So this is the solution of equation number 6. This one is 7. Now what you can get from equation 5? The equation 5, the position dependent equation, basically equation 5 can be rewritten as what you can write is as, if you see it properly, we can write it as del psi. Now if you see it here, it is only x dependent, so we can remove this del to a total derivative, d upon dx square psi of x plus 2m upon h bar square e minus v psi of x equal to 0. So this is known as the time dependent Schrodinger equation, time independent Schrodinger equation in one dimension. Okay, that's our derivation for time independent Schrodinger equation in one dimension. This our the derivation part ends here. But one thing we need to note down here: if we solve this equation, we get a solution psi x, and what phi t gives us, or the equation number 6 gives us a solution of such kind, b, let's say e to the power I e upon h bar t. So collectively we get a total solution psi of x t, just combining all constant all together, e to the a or whatever you can call the constant as, then we have psi of x e to the power, you can call it b, let's say initial constant, you can absorb it, I upon h bar into t. You can put any constant, let's say a, b, whatever, it doesn't matter. There is a total solution. So Our whole job is to solve this equation depending on the potential we have, energy or the particle or the wave function of the particle. You can find out from there. This is our whole derivation. So our time dependent Schrodinger equation is equation number 8, which you have already derived from here. So thank you for joining. We have derived in past 3 lectures how Schrodinger has derived the equation. Then you have discussed, we can simply how in an easy way you can derive the time dependent Schrodinger equation. And in this current lecture, we have discussed how we can derive the time independent Schrodinger equation. Thank you all for joining. We will proceed in our coming lectures about how we can apply Schrodinger time independent equation in different kind of systems like free particles or particles in a one-dimensional potential well. Keep on exploring and keep on learning. Thank you.